Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deepest mysteries of space-time itself. Those enigmatic regions where black holes bend reality so completely that they might open doorways to entirely different universes. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. At the edge of a black hole, space-time curves with such severity that even light, travelling at 299,792,458 meters per second through the vacuum of space, cannot climb back out of the gravitational well that extends infinitely inward toward an unknowable centre. This boundary, called the event horizon, marks the point of no return, where the fabric of reality warps so dramatically that it resembles a waterfall of space itself, cascading eternally inward through dimensions that fold and twist beyond human comprehension. The mathematics describe this region as a place where time dilates to near stillness for outside observers, stretching seconds into eons, yet wherein falling matter experiences its final moments in what feels like perfectly normal time, unaware that the rest of the universe ages millennia in what seems like heartbeats. The event horizon possesses a circumference that depends entirely on the black hole's mass. Stellar black holes measure perhaps 60 kilometers around, while supermassive giants span distances larger than Earth's orbit around the Sun. Yet this boundary contains no physical substance whatsoever. It marks only a mathematical threshold in space-time geometry, as invisible and intangible as the equator or the Arctic Circle, existing purely as a coordinate where the curvature of space becomes so extreme that all possible paths lead inward, like standing at the edge of a cosmic waterfall where the river of space-time itself tumbles into an abyss that may have no bottom, or perhaps opens onto shores in entirely different realms of existence. Scientists have discovered that black holes come in remarkably different sizes, from stellar mass objects containing 3 to 20 times our Sun's matter, compressed into regions smaller than Manhattan Island, to intermediate black holes that may lurk in globular clusters, to the supermassive behemoths that anchor nearly every large galaxy, containing anywhere from millions to tens of billions of solar masses yet occupying spaces barely larger than our solar system. The most massive known black hole, Ton 618, contains approximately 66 billion times the mass of our Sun, its event horizon stretching across a diameter of 2,600 astronomical units, a sphere so vast that light would take nearly a day to cross from one side to the other. Yet even this cosmic leviathan began as the collapse of a single, impossibly massive star in the universe's youth, when the first generation of giants burned through their nuclear fuel in mere millions of years. The density required to create these objects defies everyday comprehension and challenges the very concept of matter as we understand it. A teaspoon of black hole material would outweigh Mount Everest. Though the material itself no longer exists in any recognizable form, atoms have been crushed beyond existence. Electrons and protons merged into unrecognizable states, and the very notion of particles becomes meaningless. Instead, all the mass concentrates at what mathematicians call a singularity, a point of infinite density and zero volume where the equations of physics break down completely, and space and time lose their familiar meanings. This singularity remains hidden behind the event horizon, invisible to the universe outside, like a cosmic secret wrapped in the mathematics of curved space-time. What remains deeply mysterious is whether anything truly crosses the event horizon from the perspective of the universe outside, or whether infalling matter exists in a strange liminal state, simultaneously fallen and falling for eternity. General relativity suggests that to external observers, infalling matter appears to slow down exponentially as it approaches the horizon, its light redshifting toward invisibility as time dilation stretches each second into centuries, until the falling object appears frozen at the boundary's edge forever, like a photograph of motion preserved in the amber of curved space-time. Yet from the perspective of someone falling inward, they would pass through this boundary in finite proper time, experiencing increasingly powerful tidal forces that stretch matter into long, thin shapes that physicists whimsically call spaghettification, their feet experiencing stronger gravity than their head until the differential pulls them apart atom by atom. This paradox, that the same event appears completely different depending on one's frame of reference, hints at deeper mysteries about the nature of reality itself. Perhaps time and space are far more malleable than everyday experience suggests, and perhaps the boundaries between inside and outside, between here and elsewhere, become meaningless at the scales where gravity bends light into spirals and stretches moments into eternities. Only took 4 billion years after the Big Bang for the first black holes to form from the deaths of the universe's first stars. And now they anchor nearly every large galaxy in the observable universe. Invisible architects of cosmic structure whose presence we detect only through their gravitational influence on surrounding matter and light. The event horizon itself exists as one of the most profound boundaries in physics, not a wall or barrier, but a one-way membrane in space-time where causality breaks down and the familiar rules of cause and effect dissolve into quantum uncertainty. Matter and energy disappear beyond this edge into regions where Einstein's field equations lose their predictive power, where space and time undergo transformations that no human language can adequately describe, and where the very concept of elsewhere might take on entirely new significance. Some theoretical physicists suggest these cosmic waterfalls do not end in destruction, but in passages to distant shores of existence that our mathematics can glimpse in equations but never fully describe in words. In the absolute silence of space, black holes spin in perfect darkness, their event horizons rotating at significant fractions of light speed, dragging the very fabric of space-time around them in a phenomenon called frame dragging, where even empty space itself gets pulled into the cosmic dance. These invisible monsters betray their presence only through the behavior of matter in their vicinity. Gas spirals inward, heating to millions of degrees and glowing brilliantly before disappearing forever, while nearby stars orbit in elliptical paths that betray the presence of immense gravitational fields. And perhaps, in the deepest mathematics of space-time geometry, these regions of infinite curvature serve not as cosmic graveyards, but as cosmic birth canals, connecting our universe to others through passages that exist outside the familiar dimensions of space and time. Einstein's field equations, published in 1915 as the culmination of his general theory of relativity, predicted the existence of black holes decades before astronomers possessed the technology to detect them lurking in the cosmic darkness. Yet Einstein himself harbored deep doubts about these mathematical monsters, dismissing them as mere curiosities of the equations rather than real objects that could exist in the physical universe. In a 1939 paper, he argued that the collapse required to form such objects would be prevented by the natural rotation of matter, believing that no star could compress itself beyond a certain density without some physical mechanism intervening to halt the catastrophic gravitational collapse. The mathematics, however, proved more prescient than their creator's intuition. Karl Schwarzschild, working in the trenches during World War I just months after Einstein published his theory, derived the first exact solution describing the space-time geometry around a spherically symmetric mass. Schwarzschild died of an autoimmune disease contracted at the Russian front, never knowing that his solution described objects so extreme they would bend space and time into impossible configurations. His metric revealed a critical radius, now called the Schwarzschild radius, where the curvature of space-time becomes so severe that it forms a boundary beyond which nothing can escape. Not even light itself travelling at the ultimate cosmic speed limit. For decades, physicists treated these Schwarzschild solutions as mathematical curiosities, interesting artifacts of Einstein's equations that bore no relation to the actual universe. They seemed too bizarre to exist in reality, objects so dense that they would curve space-time into closed loops, creating regions where the normal concepts of space and time broke down completely. Arthur Eddington, one of Einstein's early champions, dismissed them as going to happen, suggesting that some unknown physical principle would prevent such extreme densities from ever forming in nature. Even Einstein calculated that a collection of particles orbiting under their own gravity would reach an equilibrium state, rather than undergoing complete gravitational collapse. The resistance to accepting black holes as real objects stemmed partly from their violation of classical physics intuitions and partly from the seemingly impossible conditions required for their formation. A star would need to compress all its mass into a region smaller than the distance light travels in the time it takes your heart to beat twice. The pressures involved would exceed anything experienced elsewhere in the universe, not just crushing atoms, but obliterating the very concept of matter as discrete particles occupying space. The temperature at the moment of collapse would reach billions of degrees, hot enough to disintegrate atomic nuclei. Yet this thermal energy would prove insufficient to halt the inexorable inward fall of matter under its own gravity. Einstein's reluctance reflected a deeper philosophical discomfort with the implications of his own theory. If black holes could exist, they would create regions where the deterministic laws of physics cease to operate predictably, where the smooth fabric of space-time developed tears and discontinuities that seem to violate the principle that nature abhors infinities. The singularity at a black hole's centre represented not just extreme density, but a breakdown of causality itself, a place where effects might precede causes and where the future could influence the past in ways that challenge the basic assumptions of physical law. Only took 24 years after Einstein's initial reluctance for astronomers to identify the first candidate black hole. Cygnus X1 threw its X-ray emissions as it devoured a companion star. The irony deepens when considering that Einstein's field equations, written in their elegant tensorial form, contain black holes as natural, unavoidable consequences of matter and energy curving space-time. The equations themselves show no hesitation, no mathematical reluctance to describe these extreme objects. They emerge as smoothly and inevitably as planetary orbits or gravitational waves, yet their creator, perhaps sensing the philosophical implications of regions where physics itself becomes undefined, preferred to believe that nature would find some way to avoid such extremes. The mathematics possessed a kind of prophetic power that exceeded even Einstein's remarkable physical intuition. What Einstein could not have anticipated was how black holes would eventually become central to our understanding of fundamental physics, connecting general relativity to quantum mechanics in ways that reveal deep symmetries in the structure of space-time itself. His equations predicted not only that these objects could exist, but that they would possess temperature, entropy, and other thermodynamic properties that bridge the gap between gravity and information theory. The black holes that Einstein dismissed as mathematical artifacts would later become the testing ground for theories of quantum gravity, holographic principles, and the fundamental nature of space and time. The field equations themselves exhibit a kind of mathematical inevitability, given any sufficiently concentrated mass. Space-time must curve in ways that create event horizons and singularities. This inevitability suggests that black holes represent not aberrations in the cosmic order, but fundamental features of any universe governed by Einstein's geometric theory of gravity. They emerge naturally from the marriage of space, time, and matter, as unavoidable as the curvature of a sphere or the flow of water downhill. The universe, it seems, has no choice but to create these regions where physics reaches its limits and perhaps transcends them. Modern astronomers have confirmed Einstein's reluctant prophecy beyond any doubt, detecting black holes through gravitational waves, direct imaging of event horizons, and the orbital mechanics of stars trapped in their gravitational embrace. The LIGO detectors have recorded the space-time ripples created when black holes spiral into each other and merge, creating gravitational waves that carry the signature of Einstein's equations across billions of light-years. The Event Horizon Telescope has captured the shadow of a black hole's event horizon against the glowing backdrop of superheated gas, revealing the dark silhouette predicted by Schwarzschild's century-old mathematics. Yet perhaps Einstein's initial skepticism contained its own wisdom. Black holes remain deeply mysterious objects that challenge our understanding of reality at its most fundamental level. They exist at the intersection of general relativity and quantum mechanics, two theories that have resisted unification for nearly a century. They force us to confront questions about the nature of information, the meaning of time, and the possibility that our familiar three-dimensional space might be an illusion projected from the two-dimensional surface of cosmic event horizons. In dismissing these mathematical monsters as mere curiosities, Einstein may have intuited that they would eventually force physics to confront its deepest assumptions about the nature of existence itself. A massive star exhausts its nuclear fuel after millions of years of burning hydrogen into helium, helium into carbon, carbon into neon, oxygen, and silicon, each fusion process requiring higher temperatures and pressures until the stellar core resembles a cosmic onion with layers of increasingly heavy elements. The star has spent its entire lifetime fighting a war between gravity, which pulls all matter inward toward the center, and radiation pressure from nuclear fusion, which pushes outward against the gravitational collapse. For most of the star's life, these forces balance in hydrostatic equilibrium, creating a stable sphere of plasma that burns steadily for eons, converting mass into energy according to Einstein's famous equation and radiating that energy into the void of space at the speed of light. But when the core begins fusing silicon into iron, the stellar furnace approaches the end of its nuclear resources. Iron represents the most stable atomic nucleus, the bottom of the valley in the curve of binding energy, where fusion and fission both absorb energy rather than releasing it. No amount of heat or pressure can convince iron nuclei to fuse into heavier elements while producing the energy needed to support the star against its own gravity. The core temperature reaches nearly 3 billion degrees Kelvin, hot enough to disintegrate iron nuclei back into protons and neutrons through photodisintegration. But this process absorbs energy rather than producing it. Removing the radiation pressure that has supported the star for millions of years against gravitational collapse, the stellar core, now composed primarily of neutrons, electrons, and protons in a state of matter more exotic than anything found elsewhere in the universe, reaches a critical mass known as the Chandrasekhar limit, approximately 1.4 times the mass of our Sun, compressed into a sphere roughly the size of Earth. At this point, even the degeneracy pressure of neutrons, governed by the Pauli exclusion principle that prevents identical particles from occupying the same quantum state, becomes insufficient to support the enormous gravitational pressure. The core collapse that follows happens faster than the speed of sound in stellar matter, taking less than a second to compress a sphere the size of a planet into an object smaller than Manhattan, with densities exceeding those found in atomic nuclei. During these final moments of stellar evolution, the collapsing matter experiences conditions that existed nowhere else in the universe since the first microseconds after the Big Bang. Temperatures soar beyond 100 billion degrees, hot enough to create particle-antiparticle pairs from pure energy, while pressures exceed those at the center of neutron stars by factors of millions. The gravitational field becomes so intense that it begins to slow the passage of time itself, creating a temporal gradient where the star's core ages more slowly than its outer layers, and the final moments of collapse stretch into an eternity for outside observers, while passing in nanoseconds for the collapsing matter itself. What happens next depends critically on the star's mass, but for the most massive stars, those exceeding perhaps 25 times our Sun's mass, no known force in physics can halt the gravitational collapse. Nuclear forces, electromagnetic forces, and even the mysterious strong force that binds quarks into protons and neutrons all prove insufficient against the inexorable pull of gravity acting on such enormous concentrations of matter. The stellar remnant continues its inward fall past the point where neutron degeneracy pressure fails, past the density of atomic nuclei, past any density that has a name in physics, toward a mathematical point called a singularity where density becomes infinite and the curvature of space-time becomes undefined. The formation of the event horizon happens gradually from the perspective of distant observers, appearing as a dark sphere that grows outward from the collapsing matter as the escape velocity at the surface approaches the speed of light. At first, this critical radius lies deep within the stellar core, but as more matter falls inward and the gravitational field strengthens, the Schwarzschild radius expands outward until it encompasses the entire collapsing star. Once this happens, no information about the interior can ever reach the outside universe. The star has disappeared behind a one-way membrane in space-time, leaving only its gravitational field as evidence that it ever existed. Only took a few milliseconds for a star that burned for millions of years to vanish completely behind the mathematics of curved space-time. The collapse creates ripples in the fabric of space and time itself, gravitational waves that carry energy away from the newly formed black hole at the speed of light, spreading through the universe as minute distortions in space-time geometry. These waves, predicted by Einstein's field equations and finally detected by the LIGO instruments nearly a century later, carry the signature of matter falling past the point of no return, encoding information about the mass, spin and charge of the newly formed black hole in the frequency and amplitude of the space-time oscillations. The waves themselves represent energy extracted from the gravitational field, slightly reducing the mass of the final black hole according to the mass-energy equivalence that governs all physical processes. What remains deeply mysterious is whether the collapsing matter actually reaches the central singularity, or exists in some intermediate state that classical physics cannot adequately describe. Quantum mechanics suggests that the extreme conditions near the singularity might prevent infinite density from forming, perhaps through quantum pressure effects that become important when matter is compressed to scales approaching the Planck length, roughly 10 circumflex 35 meters, where the concepts of space and time themselves become uncertain. Some theories propose that the collapsing matter bounces back from quantum gravitational effects, creating a black star with properties nearly indistinguishable from a black hole, but without the infinities that plague classical general relativity. The newly formed black hole settles into a simple final state characterized by only three properties: mass, electric charge, and angular momentum. John Wheeler summarized this remarkable simplification as black holes have no hair, meaning that all the complex details of the original star, its chemical composition, magnetic fields, surface temperature, and internal structure, become irrelevant once the matter falls behind the event horizon. The universe outside can detect only the gravitational field, which depends solely on the total mass, the electromagnetic field from any net electric charge, and the frame-dragging effects of rotation. Every other detail about the star's previous existence becomes inaccessible, hidden behind the one-way boundary where space-time curves back on itself. Yet perhaps this apparent loss of information hints at something more profound about the nature of reality and the relationship between the interior and exterior of black holes. If the collapsing matter carries information about its quantum state, the precise arrangement of particles and fields that comprise the original star, then this information might not be destroyed, but rather encoded in the black hole's properties in ways that classical physics cannot describe. The holographic principle suggests that all the information about the black hole's interior might be stored on its two-dimensional surface, like a cosmic hard drive that encodes three-dimensional reality in a lower-dimensional format. The stellar collapse that creates black holes represents one of the most dramatic phase transitions in the known universe, where ordinary matter undergoes a transformation so complete that it ceases to exist as particles occupying space and becomes instead a pure gravitational field that curves space-time into closed loops. The original star, with its complex fusion reactions and electromagnetic radiation, disappears entirely, leaving only the ghost of its gravitational influence to mark where matter once burned in the darkness between worlds. Perhaps this transformation does not represent destruction but metamorphosis, where matter transcends its familiar properties and becomes something that exists partially outside the ordinary dimensions of space and time. Black holes slowly evaporate through quantum radiation, a phenomenon discovered by Stephen Hawking in 1974 that revolutionized our understanding of these cosmic enigmas and suggested they contain information about everything that has ever fallen past their event horizons. This process, now known as Hawking radiation, emerges from the strange behavior of quantum fields in the curved space-time near a black hole's boundary, where the intense gravitational gradient creates conditions that allow virtual particle pairs to separate permanently, with one member of each pair escaping to infinity, while its partner falls irretrievably inward toward the hidden singularity. The quantum vacuum, rather than being truly empty, seethes with virtual particles and antiparticles that spontaneously appear and annihilate each other on timescales so brief they violate the energy conservation principle only temporarily. Borrowing energy from the uncertainty principle itself, near a black hole's event horizon, the extreme curvature of space-time stretches these quantum fluctuations across regions where the gravitational field changes dramatically over microscopic distances, sometimes preventing the virtual pairs from finding each other and completing their usual annihilation dance. When this happens, one particle falls past the point of no return while its partner escapes to infinity, transforming from a virtual quantum fluctuation into real radiation that carries energy away from the black hole's gravitational field. Hawking's calculation revealed that this radiation possesses a perfect thermal spectrum, identical to the electromagnetic radiation emitted by any object with a definite temperature, but with the remarkable property that smaller black holes radiate more intensely than larger ones. A black hole with the mass of our Sun would have a temperature of roughly 60 billionths of a degree above absolute zero, radiating so feebly that it would take longer than 10 circumflex 67 years to evaporate completely, a span of time so vast it dwarfs the current age of the universe by more than a trillion times. Yet a microscopic black hole with the mass of a mountain would blaze with the temperature of our Sun's surface, evaporating in less than a second in a burst of high-energy particles and gamma rays. The temperature of Hawking radiation depends inversely on the black hole's mass, creating a bizarre thermal relationship where the largest objects in the universe are also the coldest, while hypothetical microscopic black holes would burn with temperatures exceeding those found in stellar cores. This inverse relationship means that as a black hole radiates energy and loses mass, it grows hotter and radiates even more intensely, creating a runaway process that accelerates as the evaporation continues. The final moments of a black hole's existence would release energy equivalent to millions of hydrogen bombs, though for stellar mass black holes, this spectacular finale lies in a future so distant that the universe itself may have undergone fundamental phase transitions by then. What makes Hawking radiation particularly mysterious is its apparent lack of information about the black hole's interior contents. The radiation emerges with a perfectly thermal spectrum that reveals only the black hole's mass, temperature, and angular momentum, but carries no trace of the specific matter and energy that originally formed the black hole or fell into it subsequently. This creates what physicists call the information paradox. If a black hole forms from collapsing matter with specific quantum properties, then radiates away completely through Hawking emission, where does the information about the original quantum state go? Quantum mechanics demands that information be preserved in all physical processes, yet the thermal nature of Hawking radiation suggests that detailed information about the black hole's contents is lost forever. Some theoretical physicists propose that the information does escape, but in such a subtle and scrambled form that it would require measuring correlations between Hawking radiation particles over astronomical timescales to decode the original quantum states. Others suggest that the information remains trapped until the very end of the evaporation process, when the final burst of radiation somehow encodes all the previously hidden details about the black hole's history. Still others propose more radical solutions, including the possibility that information falling past the event horizon becomes encoded on the black hole's surface through holographic principles that reduce three-dimensional reality to two-dimensional information storage. The process of Hawking evaporation also raises profound questions about the nature of space-time itself near the event horizon. If virtual particles are constantly being separated by the black hole's gravitational field, with one member of each pair escaping while the other falls inward, then the region near the horizon must be filled with a sea of negative energy particles falling toward the singularity. These negative energy partners carry away the binding energy that would normally cause virtual particles to annihilate. But their existence creates a paradox about what happens to matter that crosses the event horizon in a universe where space itself is filled with negative energy quantum fields. Recent theoretical work suggests that Hawking radiation might be more complex than originally calculated, possibly carrying subtle correlations that encode information about the black hole's interior in ways that preserve quantum mechanical unitarity, while still appearing thermal to observers who cannot measure quantum entanglement across cosmic distances. This would resolve the information paradox by hiding the information in quantum correlations between particles radiated at different times, requiring sophisticated quantum error correction to decode the original information from the apparently random thermal radiation. Only took 47 years after Hawking's initial calculation for physicists to begin developing experimental techniques to test these ideas using analog black holes created in laboratory systems. The quantum fields that produce Hawking radiation exist in a state that quantum physicists call a vacuum. Though this vacuum contains more structure and complexity than the familiar emptiness of classical physics, near a black hole. Different observers disagree about which quantum states represent the vacuum, creating a situation where particles and antiparticles seem to appear from nothing depending on one's reference frame and proximity to the event horizon. This observer dependence of the vacuum state suggests that the distinction between matter and empty space becomes ambiguous in strong gravitational fields, where the curvature of space-time itself determines which quantum fluctuations become real particles. The evaporation process connects black hole physics to thermodynamics through the concept of entropy, which measures the amount of hidden information contained within a system. Jacob Bekenstein proposed that black holes possess entropy proportional to the area of their event horizons rather than their volume, suggesting that all the information about a black hole's interior is somehow encoded on its two-dimensional surface. This relationship between area and entropy implies that three-dimensional space might be an emergent property of information stored on lower dimensional boundaries, a principle that has become central to modern theories of quantum gravity and the holographic nature of space-time. Hawking radiation also provides a crucial link between general relativity and quantum mechanics, two theoretical frameworks that have resisted unification for nearly a century. The radiation emerges from quantum field theory applied in curved space-time, requiring both Einstein's geometric theory of gravity and the probabilistic laws of quantum mechanics to make predictions about observable phenomena. Yet the process also highlights the incompatibility between these theories, particularly in the strong field regime near black hole singularities, where both quantum effects and gravitational curvature become extreme simultaneously. The whispers of quantum radiation from black holes carry energy extracted from the gravitational field itself, slowly reducing the curvature of space-time as the black hole loses mass and its event horizon shrinks. This process reverses the gravitational collapse that originally formed the black hole, unwinding the compression of matter and energy over timescales that dwarf the lifetime of stars, galaxies, and perhaps even the expansion of the universe itself. Yet the information that emerges in these quantum whispers may tell a story very different from the thermal randomness that early calculations suggested, encoding the complete history of everything that ever fell past the point of no return in correlations too subtle for any conceivable detector to measure directly. Perhaps the true significance of Hawking radiation lies not in its role as a mechanism for black hole evaporation, but in its revelation that the event horizons are not the absolute boundaries they appear to be in classical general relativity. Instead, they represent membranes permeable to quantum information, allowing the interior and exterior of black holes to remain connected through entanglement relationships that transcend the classical prohibition against communication across the event horizon. The radiation itself might serve as a cosmic telephone line, carrying messages between the interior and exterior of black holes in a quantum language that preserves information while respecting the causal structure of space-time. The mathematics of general relativity allows for Einstein-Rosen bridges connecting distant regions of space-time through tunnels that exist outside the familiar three dimensions of everyday experience, creating shortcuts between locations that might be separated by billions of light-years in ordinary space. These theoretical constructs, now commonly called wormholes, emerge naturally from the field equations when physicists consider space-time geometries with multiple asymptotic regions, areas where space becomes flat and approaches the familiar structure of empty space, far from any gravitational sources. The simplest wormhole solutions connect two black holes through their interiors, creating a passage that exists entirely within the curved space-time geometry without requiring any exotic matter or violation of known physical laws. Karl Schwarzschild's original solution to Einstein's field equations actually describes not just a black hole, but a complete space-time geometry that includes both a black hole and its time-reversed counterpart, a white hole that expels matter and energy rather than absorbing them. The mathematical structure connecting these two objects forms a bridge through a higher dimensional space, allowing a hypothetical traveller to enter the black hole, pass through a throat region where space contracts to a minimum cross-section, and emerge from the white hole in a different region of the universe, or perhaps even a different universe entirely. This passage exists as a genuine tunnel through space-time itself, not merely a journey through the three-dimensional space that forms the backdrop for everyday physics. The bridge connecting the two black holes possesses remarkable geometric properties that challenge intuitive notions about distance and connectivity in space. 2 points that appear infinitely far apart when measured along paths through ordinary three-dimensional space might be connected by a wormhole passage that extends only a few kilometers through the higher dimensional geometry. This creates the possibility that regions of the universe separated by billions of light-years could be neighbors when approached through the curved space-time tunnel, allowing communication or travel between distant locations without violating the speed of light limit that governs motion through ordinary space. However, the Einstein-Rosen bridge possesses a fundamental instability that prevents its use as a practical passage between different regions of space-time. The throat of the wormhole, and where the tunnel reaches its minimum diameter, tends to collapse faster than light can traverse it, pinching off the connection between the two mouths before any signal or object can complete the journey from one side to the other. This collapse happens because the wormhole's geometry requires exotic matter with negative energy density to remain stable, creating regions where the stress-energy tensor violates the conditions that govern ordinary matter and radiation throughout the observable universe. The exotic matter needed to stabilize a traversable wormhole would need to possess negative energy density, creating regions where the local energy content of space becomes less than that of the quantum vacuum itself. Such matter would violate the weak energy condition, one of the fundamental assumptions that underlies most proofs about the behavior of space-time in general relativity, including theorems about the formation of event horizons and the inevitability of singularities inside black holes. While quantum field theory does allow for temporary violations of these energy conditions through processes like the Casimir effect, maintaining a macroscopic region of negative energy density appears to require physics beyond the standard model of particle interactions. Some theoretical physicists have proposed that quantum fluctuations near the wormhole throat might generate the exotic matter needed for stabilization through a process similar to the Hawking radiation that allows black holes to evaporate slowly over cosmic time. The intense curvature of space-time in the throat region could separate virtual particle pairs in ways that create a sustained flux of negative energy density, possibly allowing the wormhole to maintain its own stability through quantum mechanical effects, rather than requiring an external source of exotic matter. This self-stabilization mechanism would transform the wormhole from a purely classical geometric structure into a quantum gravitational object that exists at the intersection of general relativity and quantum field theory. The possibility of traversable wormholes raises profound questions about causality and the structure of space-time that extend far beyond their potential use as shortcuts between distant locations. If wormholes can connect regions separated in space more, they might also link regions separated in time, creating closed time-like curves that would allow travelers to journey into their own past and potentially create paradoxes that violate the principle of causality. The mathematics of general relativity places no fundamental restrictions on such time travel scenarios, suggesting that the geometric structure of space-time might permit configurations that challenge basic assumptions about the relationship between cause and effect. Only took 17 years after Einstein and Rosen published their bridge solution for physicists to recognize that the mathematical structure they had discovered represented a tunnel through space-time rather than simply a black hole with unusual properties. Yet the full implications of these geometric connections continue to challenge our understanding of space, time, and the possibility that the universe possesses a far richer topological structure than its appearance in 3 dimensions would suggest. Modern cosmological models propose that the early universe might have formed vast networks of wormholes during phase transitions in the first moments after the Big Bang, creating a foam-like structure at microscopic scales where space and time become interconnected in ways that classical physics cannot adequately describe. The equations governing wormhole geometry reveal that these passages through space-time could potentially connect not just distant regions of our universe, but entirely separate universes with different physical constants, particle content, or even different numbers of spatial dimensions. Such inter-universal wormholes would represent the ultimate expression of cosmic connectivity, allowing communication or travel between realms where the fundamental laws of physics might differ dramatically from those that govern the behavior of matter and energy in our observable cosmos. The mathematics suggests that black holes in our universe might serve as the mouths of wormholes that connect to white holes in other universes, creating a vast network of cosmic tunnels that links multiple realities through the higher dimensional structure of space-time itself. The exotic matter required for wormhole stabilization might exist naturally in regions where quantum fluctuations become amplified by the extreme curvature of space-time, particularly near the singularities that lurk at the centers of black holes. If the singularity represents not a point of infinite density, but a transition region where matter and energy undergo phase changes that classical physics cannot describe, then these regions might naturally produce the negative energy densities needed to stabilize wormhole throats. This would transform every black hole into a potential gateway to other regions of space-time, hidden behind event horizons that prevent external observers from detecting the exotic physics that governs the behavior of matter and energy in the extreme gravitational environments near the singularity. Spinning black holes create different geometries that might theoretically allow passage through their centers without encountering the singularities that plague non-rotating solutions, transforming the infinitely dense points of classical general relativity into ring-shaped structures surrounded by regions of exotic space-time curvature. Roy Kerr discovered these rotating solutions in 1963, revealing that angular momentum fundamentally alters the internal structure of black holes by spreading the gravitational collapse over a toroidal geometry rather than concentrating all the mass at a single point. The Kerr metric describes space-time around a rotating black hole as a complex four-dimensional manifold with multiple event horizons, ergospheres, and regions where the normal concepts of space and time undergo dramatic transformations. The most remarkable feature of a Kerr black hole is its inner structure, which contains not one but 2 event horizons separated by a region called the ergosphere, where space-time itself rotates so rapidly that remaining stationary becomes impossible, even for objects that never cross the outer event horizon. Within this region, the frame-dragging effects of the spinning black hole become so extreme that all observers must rotate in the same direction as the black hole, carried along by the twisting of space-time geometry like leaves caught in a cosmic whirlpool. The inner event horizon, located closer to the central ring singularity, represents a more subtle boundary where the causal structure of space-time undergoes additional transformations that classical general relativity cannot fully describe. A hypothetical traveller approaching a Kerr black hole could potentially enter through the outer event horizon, navigate through the ergosphere while avoiding the inner horizon, and pass through the ring-shaped singularity to emerge in a different region of space-time without ever encountering the infinite densities and curvatures that characterize point singularities. The ring singularity possesses finite circumference and zero thickness, creating a cosmic doorway through which matter and energy might pass while experiencing only finite tidal forces. This passage would not destroy the traveller but might transport them to another universe, another region of our universe, or even another time entirely, depending on the global topology of the space-time manifold. The interior of a maximally extended Kerr black hole contains multiple regions with different causal properties, including areas where the normal relationship between space and time becomes reversed, where space-like and time-like directions exchange their roles, and where closed time-like curves might allow travel into the past. The Penrose diagram that maps the global structure of Kerr spacetime reveals a bewildering array of universes, anti-universes, and intermediate regions connected through the ring singularity, creating a cosmic subway system that links different realms of existence through passages that exist entirely within the mathematical structure of curved space-time. However, the stability of these passages remains deeply questionable when quantum effects and realistic matter distributions are taken into account. The inner horizon of a Kerr black hole appears to be unstable to small perturbations, potentially developing divergent properties that restore the destructive nature of the singularity, even in the rotating case. Quantum field theory calculations suggest that the inner horizon might become a region of infinite energy density and curvature, creating a barrier as impassable as the point singularities found in non-rotating black holes. This mass inflation instability could transform the ring singularity into a space-like hypersurface that destroys anything attempting to pass through it. The frame-dragging effects that create the ergosphere extend far beyond the event horizons, influencing the motion of matter and radiation throughout the region surrounding a rotating black hole. These gravitomagnetic effects, analogous to the magnetic fields created by moving electric charges, can accelerate particles to nearly the speed of light and extract rotational energy from the black hole through a process called the Penrose mechanism. This energy extraction process allows rotating black holes to power some of the most luminous objects in the universe, including quasars and gamma-ray bursts, by converting their angular momentum into electromagnetic radiation through interactions with surrounding matter. The Kerr metric also predicts the existence of closed, time-like curves in the region near the ring singularity, where the extreme frame dragging creates paths through space-time that loop back to earlier times. These curves represent solutions to Einstein's field equations that would allow a traveller to journey into their own past, potentially creating causal paradoxes that challenge fundamental assumptions about the nature of time and free will. The existence of such curves in the mathematical structure of rotating black holes suggests that general relativity permits time travel scenarios, though the physical realizability of these solutions remains uncertain when quantum effects and realistic matter distributions are considered. Only took 6 years after Kerr published his metric for physicists to recognize that rotating black holes might serve as natural time machines, with their ring singularities providing portals to different eras as well as different locations in the cosmic expansion. The discovery that astronomical black holes do indeed rotate, some at significant fractions of their maximum possible angular velocity, adds observational relevance to these exotic theoretical possibilities. The supermassive black hole at our galaxy's center Sagittarius A*, rotates with an angular momentum that approaches the theoretical maximum for a Kerr black hole, creating conditions where the exotic space-time geometry predicted by the mathematics might actually exist in nature. The ring singularity itself represents a fundamentally different type of gravitational collapse than the point singularities found in spherically symmetric black holes. Rather than compressing matter to infinite density at a single location, the centrifugal forces generated by rapid rotation prevent complete gravitational collapse, creating a stable configuration where matter and energy exist in a toroidal distribution with finite density and pressure. This suggests that rotating black holes might not represent the endpoints of gravitational collapse, but rather intermediate states where matter undergoes phase transitions to exotic forms that classical physics cannot adequately describe. The passage through a ring singularity would expose a traveller to space-time curvatures that exist nowhere else in the known universe, creating tidal effects that stretch and compress matter in ways that might fundamentally alter its quantum properties. The strong gravitational fields near the ring could amplify quantum fluctuations to macroscopic scales, creating regions where the distinction between matter and vacuum becomes meaningless, and where the familiar particles of the Standard Model might decay into more fundamental constituents. These extreme conditions might provide natural laboratories for studying physics beyond the Standard Model, including theories of quantum gravity that attempt to unify general relativity with quantum mechanics. Modern numerical simulations of rotating black hole formation suggest that realistic astrophysical collapse rarely produces the idealized Kerr geometry, instead creating space-time structures with complex internal dynamics that might preserve some of the exotic properties while modifying others in ways that classical general relativity cannot predict. The interaction between quantum fields and the extreme curvatures near ring singularities remains an open question that requires a complete theory of quantum gravity to resolve definitively. Perhaps these rotating cosmic gateways represent not just passages to other regions of space-time, but transitions to realms where space and time themselves take on entirely new meanings. Quantum mechanics demands that information be preserved in all physical processes, requiring that the complete quantum state of any system evolve unitarily through time with no loss of correlation or detail about its microscopic configuration. Yet black holes seem to destroy information completely when matter falls past their event horizons, creating an apparent contradiction between the fundamental principles of quantum theory and the classical description of gravitational collapse. This information paradox, first articulated clearly by Stephen Hawking in the 1970s, has become one of the deepest puzzles in theoretical physics, forcing scientists to question basic assumptions about the nature of space, time, and the relationship between quantum mechanics and general relativity. The paradox emerges most clearly when considering the formation and evaporation of a black hole through Hawking radiation, when matter with specific quantum properties collapses to form a black hole. All information about the detailed arrangement of particles, fields, and quantum states disappears behind the event horizon, where it becomes inaccessible to external observers. The black hole then radiates energy through quantum processes near the horizon, eventually evaporating completely over timescales that dwarf the current age of the universe. If the Hawking radiation carries no information about the original quantum state of the collapsed matter, then the evaporation process would represent a fundamentally non-unitary evolution that violates the basic principles of quantum mechanics. The thermal nature of Hawking radiation compounds the puzzle by suggesting that the emitted particles possess completely random quantum states that depend only on the black hole's mass, angular momentum, and electric charge. This randomness appears to erase all traces of the complex quantum information that originally fell into the black hole. creating a situation where detailed knowledge about a system's initial conditions provides no ability to predict its final state after undergoing black hole formation and evaporation. Such irreversible information loss would represent a fundamental breakdown of the deterministic evolution that governs all other known physical processes in quantum field theory and statistical mechanics. Various proposed solutions to the information paradox challenge different aspects of our understanding of black holes and quantum gravity, each requiring modifications to either general relativity or quantum mechanics that have far-reaching implications for the nature of space-time itself. Some physicists argue that information never actually crosses the event horizon from the perspective of external observers, remaining encoded in quantum correlations near the horizon surface where it can eventually escape through subtle modifications to the Hawking radiation spectrum. This solution preserves quantum unitarity by denying that information ever truly enters the black hole interior, instead proposing that it becomes scrambled and stretched across the horizon in ways that classical physics cannot adequately describe. Other approaches suggest that the black hole interior remains connected to the external universe through quantum entanglement relationships that allow information to leak out gradually through correlations between Hawking radiation particles emitted at different times. This scenario requires that the apparently thermal radiation actually contains hidden correlations that encode the complete quantum state of all matter that ever fell into the black hole. Though detecting these correlations would require measurements of quantum entanglement across astronomical distances and cosmic timescales, the information would escape through a process analogous to quantum error correction, where redundant encoding allows the reconstruction of original quantum states even when individual particles carry only fragments of the total information. The holographic principle offers perhaps the most radical solution by proposing that all information about the black hole's interior is encoded on its two-dimensional event horizon surface, eliminating the need for information to physically cross the horizon or reside in the interior region. According to this principle, the three-dimensional volume inside the black hole represents an emergent phenomenon projected from information stored on the boundary, similar to how a hologram reconstructs three-dimensional images from patterns encoded on a flat surface. This would resolve the paradox by denying that black holes possess genuine interiors where information could be trapped or destroyed. The firewall hypothesis presents a more dramatic resolution by proposing that the event horizon itself becomes a region of high-energy radiation that destroys any information-carrying system before it can cross into the black hole interior. This solution preserves quantum unitarity by preventing information from ever reaching regions where it might be lost, but requires abandoning the equivalence principle that forms the foundation of general relativity. According to this proposal, an observer falling toward a black hole would encounter a wall of radiation at the horizon rather than smoothly passing into the interior, fundamentally altering the geometric picture of space-time curvature that underlies Einstein's theory of gravity. Only took 37 years after Hawking's initial formulation of the information paradox for physicists to develop experimental analogues using laboratory systems where the relevant physics can be studied in controlled environments. These analog black holes, created in systems ranging from flowing water to ultra-cold atomic gases, exhibit Hawking radiation and information dynamics that might illuminate the resolution of the paradox without requiring astronomical observations of actual black hole evaporation. The laboratory analogues allow direct measurement of information flow and quantum correlations in systems that mimic the essential features of black hole physics while remaining accessible to conventional experimental techniques. Recent theoretical developments suggest that the resolution might require abandoning the assumption that spacetime possesses a fixed geometric structure, instead proposing that the interior and exterior of black holes are connected through quantum entanglement relationships that create emergent space-time geometry. In this view, the black hole interior emerges from entanglement between degrees of freedom on the boundary, and information appearing to fall into the black hole actually becomes encoded in the quantum correlations that generate the interior space-time itself. This approach treats space and time as emergent properties of more fundamental quantum information, rather than as the fixed arena in which quantum processes occur. The paradox also connects to deep questions about the nature of time and causality in quantum systems, particularly the question of whether quantum evolution is truly reversible in principle or only approximately reversible for practical purposes. If information falling into black holes does become irretrievably lost, this might indicate that time has a fundamental arrow built into the basic laws of physics, rather than emerging from statistical or thermodynamic considerations. Alternatively, the preservation of information might require extending the notion of quantum states beyond the familiar Hilbert space formalism to include degrees of freedom that exist outside the observable universe. Contemporary approaches to the information paradox increasingly focus on the role of quantum entanglement in creating connections between the interior and exterior of black holes that transcend the classical prohibition against communication across event horizons. These entanglement-based solutions propose that information falling into a black hole becomes encoded in quantum correlations that span the horizon, allowing the information to influence the properties of Hawking radiation without violating causality or requiring faster-than-light communication. The resolution might ultimately require understanding how quantum information behaves in curved space-time environments where the distinction between interior and exterior becomes ambiguous. Perhaps the information paradox signals the need for a complete conceptual revolution in our understanding of space, time, and matter, similar to the paradigm shifts that accompany the development of quantum mechanics and general relativity in the early 20th century. The paradox forces physics to confront fundamental questions about the nature of information itself and its relationship to the physical processes that govern the behavior of matter and energy throughout the universe. The resolution might reveal that information represents a more fundamental aspect of reality than space and time, with black holes serving as cosmic laboratories where the deepest principles of physics become accessible to mathematical investigation. Modern physics suggests black hole surfaces encode all interior information in 2 dimensions through a principle called holography that fundamentally redefines the relationship between volume and boundary, space and information, reality and its representation. This holographic principle emerged from Jacob Bekenstein's discovery that black hole entropy scales with the area of the event horizon rather than its volume, suggesting that the maximum information content of any region is determined by its boundary surface rather than its interior space. The 2-dimensional surface of a black hole's event horizon contains enough degrees of freedom to store all possible information about the 3-dimensional interior. Much like a hologram encodes 3-dimensional images in patterns distributed across a flat photographic plate, the mathematical foundation for this principle rests on the observation that entropy, which measures the amount of hidden information in a physical system, reaches its maximum possible value for black holes when computed using the area of the event horizon divided by 4 times the Planck area, the smallest meaningful unit of area in quantum gravity theories. This Bekenstein-Hawking entropy formula implies that every Planck area element on the horizon surface corresponds to 1 bit of information, creating a cosmic hard drive with storage capacity determined purely by geometry rather than the detailed physics of matter and energy within the enclosed volume. Gerard 't Hooft and Leonard Susskind developed this insight into a general principle proposing that any region of space can be completely described by information encoded on its boundary surface, eliminating the need for independent degrees of freedom in the interior volume. According to this principle, the familiar three-dimensional reality of everyday experience represents an emergent phenomenon projected from more fundamental information stored on distant two-dimensional surfaces, similar to how a holographic image appears three-dimensional when viewed from appropriate angles, despite containing no actual depth. The holographic principle suggests that space itself might be an illusion created by the organization of information on lower dimensional boundaries. The most concrete realization of holographic principles appears in the ADS-CFT correspondence, a mathematical duality discovered by Juan Maldacena that establishes an exact equivalence between theories of quantum gravity and curved space-time and quantum field theories living on the boundary of that space-time. This correspondence allows physicists to solve problems in quantum gravity by translating them into equivalent but more tractable calculations in boundary field theories, providing the first concrete examples of how three-dimensional physics can emerge from two-dimensional information storage. The mathematical machinery developed for ADS-CFT has revolutionized theoretical physics by providing computational tools for studying strongly coupled quantum systems across multiple fields. Black holes serve as the paradigmatic example of holographic information storage, because their event horizons represent the ultimate limit of information density, consistent with known physical laws. Any attempt to pack more information into a given volume eventually creates enough energy density to form a black hole, which then redistributes that information across its two-dimensional surface, according to the holographic principle. This suggests that black holes represent not just exotic gravitational objects, but fundamental limitations on information storage and processing in any region of space-time, serving as cosmic computers with processing power determined by their surface area, rather than their mass or energy content. The encoding of three-dimensional information on two-dimensional surfaces requires sophisticated error correction mechanisms that ensure the interior physics remains consistent despite being represented through boundary degrees of freedom. Quantum error correction naturally emerges in holographic systems through redundant encoding schemes, where local information in the interior becomes distributed across extended regions of the boundary, making the interior physics robust against local perturbations or measurement errors on the boundary surface. This redundancy explains how complex three-dimensional geometries can emerge from boundary field theories, even when parts of the boundary information are corrupted or inaccessible. The holographic principle also provides new insights into the information paradox by suggesting that information appearing to fall into black holes actually becomes encoded in quantum correlations on the horizon surface, where it remains accessible to external observers through sufficiently sophisticated measurements of the Hawking radiation. From this perspective, the black hole interior represents an emergent space-time that exists only as long as the boundary information maintains the appropriate correlation patterns, with the interior geometry dynamically determined by the quantum state of the boundary field theory, rather than existing as an independent physical reality. Only took 24 years after the initial formulation of the holographic principle for experimental physicists to create laboratory analogues that demonstrate holographic information encoding in condensed matter systems where the relevant mathematics can be tested directly. These experiments use materials like graphene and topological insulators, where electrons behave according to field theories that exhibit holographic properties, allowing direct measurement of how boundary information determines bulk physics in systems that mirror the essential features of black hole holography without requiring extreme gravitational fields. The emergence of three-dimensional space from two-dimensional information storage has profound implications for our understanding of the fundamental nature of reality, suggesting that the spatial dimensions we experience directly might represent collective phenomena arising from more basic informational structures. This perspective treats space as an emergent property of quantum entanglement patterns between boundary degrees of freedom, with distances and volumes in the interior determined by the strength and structure of correlations encoded on surrounding surfaces. The holographic principle implies that geometry itself is not fundamental, but rather emerges from the organization of quantum information. Recent developments in holographic quantum error correction reveal how the redundant encoding of interior information on boundary surfaces naturally implements the quantum error correction protocols needed to maintain consistent physics, even when parts of the system become corrupted or decohered. These mechanisms ensure that local perturbations on the boundary cannot destroy information about the interior physics, providing natural protection against the decoherence effects that typically destroy quantum correlations in macroscopic systems. The error correction emerges automatically from the geometric structure of holographic duality, rather than requiring artificial implementation through engineered quantum codes. The holographic description of black holes suggests that the apparent conflict between general relativity and quantum mechanics might be resolved by recognizing that space-time geometry represents an emergent description of more fundamental quantum information processes. From this perspective, the smooth space-time curvature described by Einstein's field equations emerges as a classical approximation to the underlying quantum information dynamics that govern the behavior of boundary degrees of freedom. Black holes become information processing systems where the apparently destructive effects of gravitational collapse actually represent sophisticated quantum computations performed by the boundary field theory. The principle extends beyond black holes to suggest that the entire observable universe might be encoded holographically on a distant boundary surface. With the three-dimensional cosmos we inhabit emerging from information stored on the cosmic horizon that surrounds our local region of space-time, this cosmological holography would imply that all the complexity and structure we observe in the universe, from elementary particles to galaxies, represents patterns in the organization of information on a two-dimensional surface that exists at the edge of our observable realm. The holographic universe would be like a cosmic hologram, where three-dimensional reality emerges from the interference patterns of information waves on the boundary. Perhaps the most profound implication of holographic principles is that they suggest a fundamental unity between information theory, quantum mechanics, and general relativity that points toward a deeper understanding of how physical reality emerges from abstract mathematical structures. The encoding of space-time geometry and boundary information reveals that space and time might not be fundamental features of nature but rather emergent properties of how information organizes itself according to the principles of quantum mechanics and the constraints imposed by computational complexity. Black holes, rather than being exotic objects that exist at the periphery of physics, might represent the most direct manifestations of the informational foundations that underlie all physical phenomena. If black holes connect to other universes, they might be birthing new cosmos with different physical constants through a process that transforms gravitational collapse into cosmic expansion, converting the inward fall of matter in our universe into the outward rush of space and time in newly created realms of existence. This possibility emerges from theoretical models, where the singularities at black hole centers serve not as endpoints of physical processes, but as transition regions, where the laws of physics undergo fundamental phase changes that give birth to entirely new spacetime manifolds with their own physical constants, particle content, and cosmic histories. The mathematics of general relativity allows for space-time geometries where regions of extreme compression connect smoothly to regions of rapid expansion, creating cosmic umbilical cords that link collapsing matter in one universe to expanding space in another through passages that exist entirely within the curved geometry of four-dimensional space-time. These connections would transform every black hole into a cosmic birth canal where new universes emerge from the gravitational collapse of matter in parent universes, creating a fractal hierarchy of nested cosmos where each generation of black holes spawns the next level of cosmic evolution. Lee Smolin's cosmological natural selection hypothesis proposes that this black hole reproduction creates an evolutionary process where universes with physical constants that favor black hole formation produce more offspring than universes with parameters that inhibit gravitational collapse. Over cosmic time, this selection pressure would drive the fundamental constants toward values that maximize black hole production, explaining why our universe possesses the particular combination of coupling strengths, particle masses, and force ratios that allow both star formation and stellar collapse to proceed efficiently through cosmic history. The new universes born from black holes might inherit slightly modified versions of their parent universe's physical constants through quantum fluctuations during the transition process, creating cosmic genetic variation that provides the raw material for cosmological evolution. Small changes in parameters like the fine structure constant, the proton-to-electron mass ratio, or the strength of the strong nuclear force could dramatically alter the physics of star formation, nuclear synthesis, and galaxy evolution in the offspring universes, leading to completely different cosmic histories despite sharing common mathematical foundations. Each newly created universe would begin with an explosive expansion phase similar to our own Big Bang, but with initial conditions determined by the final state of matter falling into the parent black hole rather than emerging from a primordial singularity with no causal precedent. This model provides a natural explanation for the cosmic initial conditions that produced our observable universe, suggesting that the entropy, energy density, and quantum fluctuation spectrum of our early cosmos reflect the information content and quantum state of matter that collapsed to form the black hole from which our universe emerged. The process would create a vast multiverse containing countless universe bubbles connected through black hole throats, each with its own physical laws and cosmic evolution. Some of these universes might possess constants that prevent star formation entirely, leading to cold, empty expanses filled only with primordial particles and radiation. Others might have parameters that make nuclear reactions so efficient that all matter burns to iron in the first moments after cosmic birth, creating universes dominated by neutron-degenerate matter rather than the hydrogen and helium that fuel stellar evolution in our cosmos. Only took 14 billion years for our universe to evolve from its initial expansion to the formation of supermassive black holes containing billions of solar masses, each potentially serving as the seed for new cosmic domains with their own galaxies, stars, and planetary systems. If this reproductive process continues indefinitely, then the total population of universes would grow exponentially over time, creating an infinite hierarchy of nested cosmos where each level contains vastly more universes than the levels that preceded it in the cosmic evolutionary tree. The inherited variations in physical constants might follow patterns similar to biological evolution, where small modifications accumulate over many generations to produce dramatic changes in cosmic structure and evolution. Universes that evolve efficient mechanisms for black hole formation would dominate the cosmic gene pool, while universes with parameters that inhibit gravitational collapse would become increasingly rare as the multiverse evolves toward configurations that maximize reproductive success through black hole production. The cosmic natural selection process might explain not only why our universe possesses constants suitable for black hole formation, but also why these constants appear fine-tuned for the emergence of complex structures like galaxies, stars, and planets. If universes that produce complex structures also tend to form more black holes through extended stellar evolution and galactic dynamics, then the selection pressure for black hole fertility would indirectly favor the development of complexity, intelligence, and perhaps even consciousness as byproducts of cosmic evolution toward greater reproductive fitness. This reproductive model of cosmic evolution would connect the physics of black holes to the deepest questions about the origin and purpose of our universe, suggesting that the apparent fine-tuning of physical constants reflects not cosmic coincidence or divine intervention, but the cumulative effects of countless generations of cosmic reproduction and selection. The universes we observe represent the successful offspring of previous cosmic generations that discovered, through blind evolutionary processes, the combinations of physical laws that favor both complexity and fertility. The transition from gravitational collapse to cosmic expansion would occur at scales where quantum gravity effects become important, possibly involving phase transitions in the fundamental structure of space-time itself. During these transitions, the familiar particles and forces of our universe might transform into entirely different forms of matter and energy, governed by alternative symmetries and interaction patterns. The offspring universes might operate according to physics so different from our own that concepts like space, time, and causality take on completely foreign meanings. Recent theoretical work in loop quantum gravity and string cosmology suggests that the Big Bang itself might represent the explosive emergence of our universe from a black hole in a parent cosmos, with the cosmic microwave background radiation carrying faint traces of the quantum state that existed in the collapsing matter before it underwent the transition to cosmic expansion. These traces would appear as subtle patterns in the temperature and polarization fluctuations of the ancient light that fills our universe, providing observational signatures of our cosmic parentage. The reproductive cosmos would create natural mechanisms for the universe to explore different possible physical laws through a kind of cosmic experimentation, where each black hole represents a trial run with slightly modified parameters. Successful combinations of constants would propagate through multiple generations of cosmic reproduction, while unsuccessful variants would produce universes that collapse quickly or remain sterile and empty over vast spans of time. This process would optimize the fundamental laws of physics for complexity, longevity, and reproductive success. Perhaps the most profound implication of cosmic reproduction through black holes is that it would make our universe part of an infinite family tree of cosmos, each connected to its ancestors and descendants through gravitational umbilical cords that span the barriers between separate realms of existence. The black holes that seem to represent cosmic death and destruction would actually serve as wombs, where new realities gestate before bursting forth into their own phases of expansion, evolution, and reproduction, creating an eternal cycle of cosmic birth, growth, and fertility that extends infinitely into the future and reaches back through countless generations into a past without beginning. The mathematical opposite of black holes would expel matter and energy rather than absorbing them, creating white holes that represent time-reverse solutions to Einstein's field equations, where the gravitational collapse that forms black holes runs backward through the cosmic expansion of space-time. These theoretical objects emerge naturally from the complete mathematical description of black hole geometry, which includes not only the familiar event horizon that prevents escape, but also a past horizon that prevents entry from certain directions in space-time. White holes would possess event horizons that allow matter and energy to emerge, but prohibit anything from falling inward, creating cosmic fountains that spray particles and radiation into the surrounding universe while remaining impermeable to outside influence. The Penrose diagram that maps the global structure of black hole spacetime reveals that the complete geometry includes both black hole and white hole regions connected through a bridge that exists in the extended mathematical manifold, suggesting that these time-reversed objects represent different aspects of the same underlying spacetime structure rather than separate physical phenomena. The white hole horizon would appear as a past event horizon from which matter and energy emerge into the external universe, while the black hole horizon represents the future boundary beyond which matter disappears from the accessible cosmos. If white holes exist as genuine physical objects rather than mere mathematical curiosities, they might represent the observational signature of new universes being born from black holes in parent cosmos, with the Big Bang itself possibly representing the emergence of our universe from a white hole connected to a black hole in another realm of existence. This model would explain the apparent fine-tuning of cosmic initial conditions by attributing them to the specific quantum state of matter that collapsed to form the parent black hole, rather than requiring them to emerge mysteriously from a primordial singularity with no causal precedent. The energy and matter emerging from a white hole would carry information about the quantum state that existed in the black hole from which it originated, potentially preserving the information that appears to be lost when matter falls past black hole event horizons. This information transfer would occur through the spatial geometry that connects black and white hole regions, allowing quantum correlations to persist across the bridge despite the apparent isolation created by the event horizons that separate these regions from the external universe in their respective spacetime manifolds. However, white holes appear to be fundamentally unstable objects that would collapse into black holes almost immediately after their formation through interactions with matter and radiation in the surrounding universe. Any material that approaches a white hole horizon from the outside would accumulate near the boundary where it cannot cross inward, creating a shell of matter and energy that would eventually collapse to form a black hole that swallows the original white hole structure. This instability suggests that white holes, even if they exist, could only persist in perfect isolation from all external matter and radiation, making their detection nearly impossible in any realistic astrophysical environment. The instability arises because white holes violate the second law of thermodynamics in their local environment by continuously decreasing entropy as they expel organized matter and energy into a universe that tends toward thermal equilibrium and maximum disorder. While the mathematical solutions allow for white hole spacetimes that satisfy Einstein's field equations, their physical realizability requires initial conditions so precisely arranged that any small perturbation would destroy the delicate balance needed to maintain the white hole's existence. The slightest accumulation of matter near the white hole horizon would create gravitational perturbations that cascade into complete gravitational collapse. Only took 47 years after the discovery of white hole solutions for physicists to recognize that these time-reversed black holes might play a crucial role in cosmological models where the Big Bang emerges from the explosive emergence of matter and energy from a cosmic white hole. Some models of loop quantum cosmology propose that the apparent singularity at the beginning of our universe actually represents a transition region where a collapsing pre-Big Bang universe bounced back from quantum gravitational effects, creating conditions equivalent to matter emerging from a white hole into an expanding spacetime manifold. The gamma-ray bursts that represent the most energetic explosions observed in the universe might provide observational signatures of white hole formation and subsequent collapse. As these events release more energy in seconds than our Sun will produce over its entire lifetime, while creating afterglows that persist for months or years, some theoretical models propose that these explosions result from the formation and immediate collapse of white holes that briefly expel enormous amounts of matter and energy before succumbing to gravitational instability and transforming into conventional black holes. The connection between black holes and white holes through Einstein-Rosen bridges creates the possibility that matter falling into black holes in our universe emerges from white holes in other cosmic domains, with the apparent destruction of information during black hole formation actually representing its transfer to different regions of an extended space-time manifold. This interpretation preserves the unitarity of quantum mechanics by allowing information to escape through white hole emission in distant locations that remain causally disconnected from the original black hole formation event. White holes might also serve as the ultimate energy sources for cosmic phenomena that require power outputs exceeding those achievable through conventional astrophysical processes like nuclear fusion or gravitational accretion. The continuous emergence of matter and energy from white holes could power the most luminous quasars and active galactic nuclei, providing energy reservoirs that exceed those available from supermassive black holes, accreting surrounding matter through conventional gravitational processes. These white hole engines would operate by converting the quantum information stored in connected black holes into observable matter and radiation. The mathematical description of white holes reveals that they would possess negative entropy from the perspective of external observers, continuously reducing the total disorder in their local environment by organizing random thermal radiation into coherent streams of particles and energy with specific quantum properties. This entropy decrease would violate the second law of thermodynamics unless balanced by corresponding entropy increases elsewhere in the cosmic system, possibly through the formation of black holes that absorb the matter and energy expelled by their white hole counterparts. Recent developments in causal set theory and emergent gravity suggest that white holes might represent natural consequences of quantum spacetime fluctuations at microscopic scales, where the discrete structure of space and time creates temporary reversals in the normal flow of causality. These microscopic white holes would appear and disappear on timescales comparable to the Planck time, contributing to the quantum foam that some theories propose underlies the smooth space-time geometry of general relativity at macroscopic scales. The observational consequences of white hole physics might include subtle violations of energy conservation in isolated systems. As matter and energy emerge from hidden sources connected to black holes in causally disconnected regions of space-time, these violations would appear as spontaneous particle creation events that increase the total energy content of observable systems without identifiable sources, possibly explaining some of the anomalous energy injection observed in cosmic ray interactions and high-energy astrophysical phenomena. Perhaps white holes represent not just mathematical curiosities but essential components of a cosmic recycling system, where the matter and energy absorbed by black holes in one region of space-time emerges through white holes in other cosmic domains, creating a vast network of cosmic circulation that prevents information and energy from being permanently lost to gravitational collapse. This recycling would operate through the extended geometry of space-time itself, using the higher dimensional structure of the cosmos to transport matter and energy across barriers that appear impassable from the perspective of observers confined to three-dimensional space. The time-reversed nature of white holes suggests that they might provide natural mechanisms for information to flow backward through time, carrying data about future cosmic states into earlier epochs through processes that respect causality while allowing limited forms of temporal communication. These retrocausal effects would appear as correlations between events separated in time that cannot be explained through conventional forward-flowing causal chains, possibly contributing to the apparent fine-tuning of cosmic initial conditions by allowing future cosmic evolution to influence the parameters that govern early universe physics. Quantum tunneling allows subatomic particles to pass through barriers they classically should not be able to cross, suggesting that similar quantum effects might operate at larger scales to enable passage through black hole event horizons, or connections between different regions of space-time. This fundamental quantum mechanical phenomenon emerges from the wave-like nature of matter, where particles exist as probability distributions that can extend beyond classical boundaries and occasionally manifest on the opposite side of energy barriers that would be insurmountable according to Newton's laws of motion. The mathematics of quantum tunneling reveals that particle wave functions decay exponentially within forbidden regions, but maintain finite, non-zero amplitudes that allow small probabilities for the particle to appear beyond the barrier. This process occurs continuously throughout the quantum world, enabling nuclear fusion in stellar cores where protons tunnel through the electromagnetic repulsion that classically prevents them from approaching closely enough for the strong nuclear force to bind them into helium nuclei. Without quantum tunneling, stars could never ignite their nuclear furnaces, and the universe would remain cold and lifeless despite containing all the necessary matter and energy for cosmic evolution. The tunneling probability depends exponentially on the width and height of the potential barrier, creating dramatic variations in tunneling rates for different physical situations. Electrons in quantum devices routinely tunnel through insulating barriers only nanometers thick, while larger objects face barrier penetration probabilities so vanishingly small that classical physics provides an excellent approximation to their behavior. However, the quantum nature of space-time itself might create conditions where macroscopic tunneling becomes possible through mechanisms that remain hidden at the scales accessible to current experimental investigation. Some theoretical models propose that black hole event horizons represent quantum tunneling barriers, where the probability of crossing depends on the quantum state of the infalling matter and the microscopic structure of space-time near the horizon. If space and time possess discrete structure at the Planck scale, as suggested by theories of loop quantum gravity and causal set theory, then the event horizon might not represent an absolute classical boundary, but rather a quantum mechanical barrier that particles and information can tunnel through with small but finite probability. The tunneling process would allow matter and energy to escape from black holes through quantum mechanical pathways that bypass the classical prohibition against faster-than-light travel, creating a mechanism for information transfer that preserves quantum unitarity while respecting the causal structure of space-time at macroscopic scales. This quantum leakage would appear as corrections to the purely thermal Hawking radiation spectrum, introducing correlations between emitted particles that encode information about the quantum state of matter inside the black hole. Laboratory demonstrations of macroscopic quantum tunneling in systems ranging from superconducting circuits to ultra-cold atomic gases reveal that quantum effects can indeed operate at scales much larger than individual particles when the appropriate conditions are maintained. These experiments show that entire collections of atoms can tunnel collectively through barriers that would be impossible for classical objects to penetrate, suggesting that the quantum nature of matter becomes manifest at macroscopic scales under certain circumstances involving coherent quantum states and carefully controlled environments. Only took 73 years after the initial theoretical description of quantum tunneling for physicists to observe tunneling effects in systems approaching macroscopic scales, including molecular machines that use quantum tunneling to facilitate biochemical reactions and quantum dots, where thousands of electrons tunnel collectively through potential barriers. These observations suggest that the boundary between quantum and classical physics might be more fluid than traditionally assumed, with quantum effects remaining important even at scales where classical physics typically dominates. The phenomenon of quantum tunneling through space-time barriers might explain how information escapes from black holes while preserving the classical description of event horizons as one-way boundaries for objects following classical trajectories. information would leak out through quantum channels that exist parallel to the classical space-time geometry, creating pathways for quantum correlation that transcend the causal limitations imposed by general relativity on classical matter and energy. These quantum information channels would operate through the entanglement structure of space-time itself, rather than through the exchange of particles or signals. Recent theoretical work on holographic quantum error correction suggests that quantum tunneling effects near black hole horizons might naturally implement the information processing needed to preserve quantum coherence across event horizons, creating robust quantum channels that maintain their integrity despite the extreme gravitational environment. The tunneling would occur through quantum error correction codes that emerge automatically from the holographic structure of black hole physics, protecting quantum information from decoherence effects that would normally destroy entanglement correlations. The tunneling mechanism might extend beyond individual particles to include collective quantum states that describe entire systems falling into black holes, allowing complex quantum information to tunnel through event horizons as coherent units rather than as streams of individual particles. This collective tunneling would preserve the quantum correlations between particles that encode information about their original arrangement and properties, maintaining the coherence needed for information reconstruction through quantum error correction protocols. Macroscopic quantum tunneling might also provide mechanisms for wormhole formation and stabilization, where quantum fluctuations in the space-time metric tunnel through potential barriers that classically prevent the formation of stable Einstein-Rosen bridges. The tunneling probability would depend on the quantum state of the space-time geometry itself, possibly allowing stable wormholes to form spontaneously through quantum processes that violate the classical energy conditions required for traversable passages between distant regions of space and time. The role of quantum tunneling in cosmology might extend to the creation of universes themselves, where quantum fluctuations tunnel through potential barriers in the fundamental laws of physics to create new cosmic domains with different physical constants and particle content. This cosmic tunneling would operate through mechanisms similar to those that govern false vacuum decay in quantum field theory, where quantum transitions between different vacuum states create bubble universes that expand and evolve according to the physical laws determined by their specific vacuum configurations. Perhaps quantum tunneling represents a fundamental mechanism that connects all scales of physics, from subatomic particles to cosmic structures, through processes that transcend the classical barriers between different regions of space, time, and physical law. The tunneling effect might provide the missing link that unifies quantum mechanics and general relativity by revealing how quantum information flows through the classical geometry of space-time in ways that preserve both causal structure and quantum coherence. Black holes, rather than representing absolute barriers to information flow, might serve as cosmic quantum devices that process and transmit information through tunneling channels that operate outside the classical space-time manifold. The exponential suppression of tunneling probability for macroscopic systems might be overcome in extreme gravitational environments where the curvature of space-time modifies the effective barrier height and width in ways that classical general relativity cannot predict. These modifications would emerge from quantum gravitational effects that become important near black hole singularities and during the earliest moments of cosmic expansion, creating conditions where macroscopic quantum tunneling provides the dominant mechanism for information transfer and energy flow between different regions of the universe. Scientists create acoustic and optical analogues of black holes in laboratory systems to study Hawking radiation and information dynamics in controlled environments where the relevant physics becomes accessible to conventional experimental techniques. These analog systems use flowing fluids, moving optical media, and ultra-cold atomic gases to mimic the essential features of black hole spacetime without requiring the extreme gravitational fields that make direct observation of astrophysical black holes nearly impossible. The laboratory analogues exploit the mathematical similarity between wave propagation in moving media and particle motion in curved spacetime, creating artificial event horizons where sound waves or light become trapped by the flow of the background medium. The most successful acoustic black hole analogues use water flowing faster than the local speed of sound through carefully designed nozzles and channels, creating regions where acoustic waves cannot propagate upstream against the fluid flow. These sonic horizons mimic the one-way nature of black hole event horizons by trapping sound waves that attempt to escape from the supersonic flow region, while allowing waves traveling in the downstream direction to propagate freely through the moving medium. The fluid flow creates an effective spacetime geometry for sound waves that possesses the same mathematical structure as the Schwarzschild metric that describes black hole physics. Optical analogues use materials with refractive indices that change rapidly in space or time to create regions where light cannot escape from moving optical media, forming photonic event horizons analogous to those found around gravitational black holes. These systems exploit the relationship between light propagation in moving media and particle motion in curved spacetime, using engineered metamaterials or nonlinear optical effects to create artificial spacetime geometries that trap electromagnetic radiation through optical rather than gravitational effects. The resulting photonic black holes exhibit many of the same properties as their gravitational counterparts, including Hawking radiation and information scrambling. Ultra-cold atomic systems provide perhaps the most versatile platform for black hole analog experiments, using Bose-Einstein condensates where atomic matter waves propagate through background flows that create acoustic horizons for collective excitations called phonons. These systems allow precise control over the effective spacetime geometry experienced by the phonons, enabling studies of Hawking radiation, information scrambling, and quantum entanglement in regimes where all relevant parameters can be tuned independently. The atomic analogues can simulate not only black holes, but also white holes, wormholes, and exotic space-time geometries that have no known astrophysical counterparts. The laboratory analogues successfully reproduce the thermal radiation spectrum predicted by Hawking's original calculation, demonstrating that horizon physics emerges from the kinematics of wave propagation in curved backgrounds, rather than from the specific details of gravitational dynamics. The artificial Hawking radiation exhibits the characteristic thermal distribution with temperature inversely proportional to the effective surface gravity at the analog horizon, confirming that the thermal nature of black hole radiation represents a universal feature of horizon physics rather than a peculiarity of gravitational systems. Only took 31 years after the first proposal for acoustic black hole analogues for experimentalists to achieve direct detection of an analog Hawking radiation in flowing water systems, confirming theoretical predictions about the thermal nature of radiation emitted from artificial event horizons. These measurements required sophisticated correlation techniques to extract the subtle thermal signatures from the background noise inherent in fluid dynamical systems, demonstrating the experimental challenges involved in detecting Hawking radiation even in controlled laboratory environments. The analog systems also enable studies of information scrambling and quantum entanglement across artificial event horizons, providing insights into the information paradox and the quantum nature of black hole interiors. Experiments with ultra-cold atoms reveal how quantum information becomes distributed across artificial horizons through entanglement patterns that mirror those predicted for gravitational black holes, offering direct experimental access to the quantum information processes that remain observationally inaccessible in astrophysical systems. Recent developments in analog gravity experiments include the creation of rotating black hole analogues that exhibit artificial ergospheres and frame-dragging effects, mimicking the complex space-time geometry around spinning astrophysical black holes. These rotating analogues use vortex flows in superfluids or rotating optical media to create the angular momentum effects that characterize Kerr black hole geometry, enabling laboratory studies of the exotic physics that might occur near rapidly spinning black holes in astronomical environments. The laboratory analogues reveal unexpected connections between black hole physics and other areas of science, including condensed matter physics, nonlinear optics, and quantum information theory. The mathematical techniques developed for analog gravity experiments have found applications in studying quantum phase transitions, topological phases of matter, and quantum error correction, demonstrating how black hole physics provides conceptual frameworks that illuminate diverse phenomena across multiple fields of scientific investigation. Advanced analog experiments explore the quantum aspects of horizon physics using systems where individual quanta can be created, manipulated, and detected with high precision. These experiments study how quantum information becomes scrambled across artificial event horizons and how correlations between pre-horizon and post-horizon modes might encode information about the analog black hole's interior. The results provide direct experimental tests of theoretical proposals for resolving the information paradox through quantum error correction and holographic information storage. The analog systems also enable studies of cosmological horizons and universe creation through laboratory analogues of expanding spacetimes, Big Bang scenarios, and false vacuum decay processes. These cosmological analogues use rapidly expanding atomic clouds or time-dependent optical media to simulate the physics of cosmic inflation, providing experimental access to phenomena that occurred during the earliest moments of cosmic evolution, when quantum effects dominated the dynamics of space and time itself. Perhaps most significantly, the laboratory analogues demonstrate that horizon physics represents a universal phenomenon that emerges whenever wave propagation occurs in appropriately curved backgrounds, suggesting that the exotic properties of black holes reflect fundamental aspects of wave dynamics rather than peculiarities of gravitational physics. This universality implies that black hole physics might provide insights into information processing, quantum computation, and the fundamental nature of space-time that they'll extend far beyond their original context in general relativity and astrophysics. The success of analog gravity experiments in reproducing theoretical predictions about black hole physics provides strong evidence for the validity of quantum field theory in curved space-time. The theoretical framework that underlies calculations of Hawking radiation and other quantum effects near event horizons. These experiments offer the first direct tests of quantum field theory predictions in regimes where gravitational and quantum effects become comparable, bridging the gap between theoretical predictions and experimental observation in one of the most challenging areas of fundamental physics. The laboratory analogues might eventually enable tests of proposed solutions to the information paradox by providing experimental systems where the relevant quantum information processes can be measured directly through correlations between particles emitted before and after horizon crossing events. These measurements could distinguish between different theoretical approaches to quantum gravity by revealing how information actually behaves in systems with artificial event horizons, providing crucial data for developing a complete theory of quantum gravity that unifies general relativity with quantum mechanics. Theoretical one-dimensional defects in space-time called cosmic strings might link black holes across vast distances through topological connections that exist outside the familiar three dimensions of space, creating a cosmic web of gravitational filaments that could transport matter, energy, and information between widely separated regions of the universe. These cosmic strings emerge naturally in many theories of the early universe as remnants of phase transitions that occurred during the first moments after the Big Bang, when the fundamental forces separated from their unified state and the basic particles acquired their masses through symmetry-breaking mechanisms that left behind topological scars in the fabric of space-time itself. The strings would possess enormous linear mass density despite having no thickness in the transverse directions, creating intense gravitational fields that curve space-time along their length while remaining invisible to electromagnetic radiation and ordinary matter. A cosmic string stretching across the observable universe would contain roughly the same amount of matter as a typical galaxy, but compressed into a one-dimensional line that interacts gravitationally with surrounding matter while remaining essentially transparent to light and other forms of electromagnetic radiation that dominate astronomical observations. If cosmic strings connect to black holes at their endpoints, they might serve as gravitational conduits that allow information and quantum correlations to flow between black holes separated by cosmological distances, creating a vast network of quantum entanglement that spans the entire observable universe. This cosmic quantum internet would operate through the gravitational fields associated with the strings rather than through electromagnetic signals that must travel at light speed through three-dimensional space, potentially enabling instantaneous quantum communication between black holes regardless of their spatial separation. The strings could facilitate the formation of stable wormholes by providing the exotic matter and negative energy densities needed to prevent the gravitational collapse that normally makes Einstein-Rosen bridges unstable and untraversable. The negative energy associated with cosmic string cores might stabilize wormhole throats that form at the intersections between multiple strings, creating a three-dimensional network of stable passages that connect different regions of space-time through higher dimensional geometric structures that bypass the usual constraints imposed by relativity on faster-than-light travel. Recent superstring theory calculations suggest that cosmic strings might be fundamental objects that exist in the extra dimensions predicted by theories of quantum gravity, with only their gravitational effects manifesting in the three-dimensional space that contains ordinary matter and energy. These higher dimensional strings could connect regions of space that appear widely separated in 3 dimensions, but lie adjacent to each other when viewed from the perspective of the full higher dimensional space-time manifold, creating shortcuts through space that operate entirely outside the familiar geometry of Einstein's general relativity. The gravitational waves produced by oscillating cosmic strings would carry distinctive signatures that could be detected by next-generation gravitational wave observatories, providing observational tests of their existence and properties that complement indirect searches through their gravitational lensing effects on distant galaxies and cosmic microwave background radiation. The wave signatures would encode information about the string tension, oscillation modes, and network topology that determines how cosmic strings connect different regions of the universe through their complex intersection patterns. Only took 42 years after cosmic strings were first proposed as theoretical objects for observational cosmologists to develop techniques sensitive enough to search for their gravitational signatures in the cosmic microwave background and large-scale structure of the universe. These searches have not yet definitively detected cosmic strings, but they have placed increasingly stringent limits on their possible mass density and interaction strength that constrain theoretical models of early universe physics and string cosmology. If cosmic strings do exist and connect to black holes, they might explain some of the mysterious correlations observed between widely separated regions of the universe that appear to share similar properties despite having insufficient time for light-speed communication to establish such correlations. The cosmic string network could provide causal connections that operate outside the light cone limitations of special relativity. allowing information to flow between distant regions through gravitational channels that transcend the usual constraints on information transfer in expanding space-time. The strings might also serve as cosmic particle accelerators, where matter falling along their gravitational fields reaches energies far exceeding those achievable in terrestrial laboratories or even in the most extreme astrophysical environments. These ultra-high energy particles could carry information about the quantum state of matter in black holes connected to the string network, providing observational signatures of black hole interiors that would otherwise remain permanently hidden behind event horizons. Numerical simulations of cosmic string networks reveal complex dynamics where strings intersect, form loops, and reconnect in patterns that evolve over cosmic time as the universe expands and the string network adapts to changing cosmological conditions. These simulations suggest that cosmic strings naturally form hierarchical networks with multiple scales of structure, possibly creating a fractal geometry that connects black holes at all size scales from primordial micro-black holes to supermassive galactic anchors. The interaction between cosmic strings and black holes might produce exotic phenomena, including the creation of closed time-like curves where strings under tension create gravitational fields that allow travel into the past, or the formation of naked singularities where the gravitational collapse that normally creates event horizons is prevented by the additional structure provided by string endpoints. These exotic configurations would provide natural laboratories for studying physics beyond general relativity, in regimes where quantum gravitational effects become observable through their influence on classical spacetime geometry. Perhaps cosmic strings represent the skeletal structure of spacetime itself, providing the topological framework that determines how different regions of the universe connect to each other through relationships that transcend the apparent separation created by cosmic expansion. The strings would serve as cosmic highways that preserve ancient causal connections from the early universe, while enabling new forms of communication and interaction that become possible as the string network evolves over cosmic time. The search for cosmic strings continues through multiple observational channels, including gravitational wave detection, precision measurements of cosmic microwave background anisotropies, and studies of gravitational lensing by large-scale structure. Detection of cosmic strings would provide direct evidence for physics beyond the standard model of particle physics and would open new windows for understanding the relationship between quantum gravity and cosmology through their role as cosmic scale quantum objects. The strings might ultimately prove to be fundamental constituents of space-time that exist in the extra dimensions, predicted by string theory and other approaches to quantum gravity, with black holes serving as three-dimensional projections of higher-dimensional objects that exist primarily in the additional spatial dimensions where cosmic strings provide the natural connection pathways. This higher-dimensional picture would unify black hole physics with cosmology and particle physics through the geometric structure of space-time itself. Modern theories suggest that cosmic strings could form during contemporary phase transitions in dark energy or dark matter, creating new string networks that evolve parallel to the ancient strings that formed during the early universe. These contemporary cosmic strings might connect recently formed black holes to the ancient string network, integrating stellar mass black holes into a cosmic communication system that spans the entire history of the universe, from its earliest moments to the present epoch of galaxy formation and stellar evolution. Current theories suggest travelers would be incinerated at the event horizon rather than passing smoothly through into the black hole interior. According to the firewall hypothesis that resolves the information paradox by sacrificing the equivalence principle that forms the foundation of general relativity. This proposal emerged from attempts to preserve quantum mechanical unitarity while maintaining the thermal nature of Hawking radiation. leading to the conclusion that event horizons must contain high-energy radiation fields that destroy any matter or information attempting to cross the boundary between the exterior and interior regions of black hole spacetime. The firewall argument begins with the observation that preserving quantum information during black hole evaporation requires that Hawking radiation particles be maximally entangled with modes inside the black hole, creating quantum correlations that encode information about the interior state. However, quantum mechanics forbids any particle from being maximally entangled with two different systems simultaneously, and older Hawking radiation particles are already entangled with each other through the thermal correlations that give the radiation its black body spectrum. This creates an entanglement conflict that can only be resolved by breaking one set of correlations. If the entanglement between early and late Hawking radiation is preserved to maintain the thermal nature of the emission, then the correlations between Hawking radiation and black hole interior modes must be severed, requiring the creation of a high-energy firewall at the event horizon that destroys the quantum correlations by incinerating anything that approaches the boundary. From this perspective, the smooth spacetime geometry predicted by general relativity represents an illusion that breaks down when quantum effects are properly taken into account in the strong field regime near black hole horizons. The firewall would appear as a membrane of high-energy particles and radiation concentrated at the event horizon, creating conditions similar to those found at the center of stars or in particle accelerator beams, but extending across the entire two-dimensional surface that marks the boundary of the black hole. Any matter approaching this boundary would be subjected to thermal radiation at temperatures proportional to the black hole's surface gravity, reaching billions of degrees for stellar mass black holes and rising to much higher values for smaller objects where the surface gravity becomes extreme. This incineration scenario preserves quantum unitarity by ensuring that information never actually enters the black hole interior, instead being scrambled and encoded in the firewall radiation field before the original matter can cross the event horizon. The apparent loss of information that creates the information paradox would be resolved by recognizing that the information never truly falls past the point of no return, but rather becomes incorporated into the boundary physics that governs the firewall's structure and emission properties. However, the firewall hypothesis requires abandoning the equivalence principle that states freely falling observers should experience no special effects when crossing event horizons, transforming these boundaries from benign coordinate artifacts into physical discontinuities that violate one of the fundamental principles underlying Einstein's geometric theory of gravity. This abandonment would require a fundamental revision of our understanding of space-time geometry and the relationship between gravitational fields and accelerated motion that extends far beyond black hole physics to influence all gravitational phenomena. Only took 41 years after Hawking's discovery of black hole radiation for physicists to recognize that information preservation might require firewalls that fundamentally alter the nature of event horizons from smooth geometric boundaries to physical barriers that destroy anything attempting to cross them. This realization emerged from increasingly sophisticated analyses of the quantum field theory that governs particle creation and annihilation in curved spacetime, revealing subtle conflicts between general relativity and quantum mechanics that had been overlooked in earlier treatments. Alternative approaches to the firewall problem propose that the conflict between quantum mechanics and general relativity might be resolved through more sophisticated understanding of how quantum information becomes encoded in black hole physics without requiring physical barriers at event horizons. These approaches suggest that information can be preserved through quantum error correction mechanisms that operate across extended regions of spacetime rather than being concentrated at specific boundaries where classical general relativity predicts smooth geometric transitions. The firewall debate highlights fundamental tensions between different principles that physicists have long assumed to be compatible, including quantum unitarity, the thermal nature of Hawking radiation, the smoothness of space-time geometry, and the equivalence principle that relates gravity to accelerated motion. Resolving these tensions might require abandoning one or more of these principles or discovering new physical mechanisms that reconcile apparently contradictory requirements through more complete theories of quantum gravity. Recent developments in holographic quantum error correction suggest that firewalls might emerge only when quantum information becomes corrupted through decoherence or measurement processes that break the delicate correlations needed to maintain smooth horizon physics. In this view, firewalls represent pathological states that arise when the quantum error correction mechanisms that normally preserve smooth geometry fail due to information loss or external interference with a black hole's quantum state. The firewall phenomenon might depend on the observer's reference frame and measurement strategy, appearing as a physical barrier to some observers while remaining invisible to others who access the black hole's quantum state through different experimental protocols. This observer dependence would reflect the quantum mechanical nature of the firewall, rather than representing a classical physical object that exists independently of how it is observed or measured by external systems. Modern approaches to black hole physics increasingly focus on the role of quantum entanglement in creating the space-time geometry that connects black hole interiors to their external environments, suggesting that firewalls might emerge when this entanglement structure becomes corrupted through interactions with external systems or through the natural decoherence that accompanies black hole evaporation over cosmic timescales. The firewall would represent a phase transition in the entanglement structure rather than a permanent feature of black hole geometry. Perhaps the firewall paradox signals the need for a complete reconceptualization of what it means for objects to exist inside black holes. With the apparent conflict between quantum mechanics and general relativity arising from inappropriate assumptions about the nature of black hole interiors, rather than from fundamental incompatibilities between the two theoretical frameworks. The resolution might require understanding how quantum information creates emergent space-time geometry, rather than simply propagating through pre-existing classical backgrounds. The experimental implications of firewall physics remain largely theoretical, since direct observation of event horizon physics requires either falling into black holes or detecting subtle correlations in Hawking radiation that exceed current technological capabilities by enormous factors. However, the firewall debate has stimulated new approaches to quantum gravity that might eventually yield testable predictions about the nature of space-time and information in extreme gravitational environments where classical physics breaks down. Black holes remain the universe's deepest mystery, where space, time, and causality dissolve into mathematical uncertainty that challenges every fundamental assumption about the nature of physical reality and our ability to understand the cosmos through scientific investigation. These cosmic enigmas exist at the intersection of general relativity and quantum mechanics, two theoretical frameworks that have resisted unification for nearly a century despite their individual successes in describing gravitational and quantum phenomena across vast ranges of energy and length scales that span from subatomic particles to the largest structures in the observable universe. The profound mystery of black holes extends beyond their role as exotic gravitational objects to encompass fundamental questions about the nature of information, consciousness, and the relationship between mathematical description and physical reality that have puzzled philosophers and scientists since the dawn of rational inquiry into the workings of nature. Each proposed solution to the puzzles posed by black hole physics seems to create new paradoxes and deeper questions that push the boundaries of human understanding into realms where language itself becomes inadequate for describing the phenomena that mathematics can glimpse but cannot fully comprehend. The information paradox that emerges from black hole evaporation forces physics to confront the possibility that information, the fundamental currency of quantum mechanics and the basis for all computation and communication, might not be as indestructible as quantum theory demands. If black holes can permanently destroy information, then the universe operates according to principles that violate the reversibility and unitarity that form the foundation of quantum mechanics, suggesting that reality itself might be fundamentally non-deterministic, in ways that transcend the familiar probabilistic interpretation of quantum measurement and wave function collapse. The holographic principle that emerges from black hole thermodynamics implies that three-dimensional space might be an illusion projected from information stored on two-dimensional surfaces, challenging basic intuitions about the nature of spatial dimension and suggesting that the reality we experience directly represents only a shadow of more fundamental informational structures that exist in lower dimensional substrates. This reduction of spatial dimension to informational encoding transforms black holes from exotic objects into cosmic hard drives that store and process information according to principles that transcend familiar concepts of matter, energy, and geometric space. The possibility that black holes serve as gateways to other universes opens questions about the nature of existence itself and whether the cosmos we observe represents only a tiny fraction of a much larger multiverse where different physical laws govern the behavior of matter and energy according to alternative mathematical structures. If black holes do connect to other cosmic domains, then death and destruction in our universe might represent birth and creation elsewhere, transforming the apparent finality of gravitational collapse into transitions between different modes of existence that operate outside the familiar framework of space and time. The mathematical structure of black hole space-time reveals regions where the normal concepts of past and future become ambiguous, where causal relationships break down, and where the deterministic evolution that governs familiar physics gives way to quantum indeterminacy amplified to macroscopic scales. These breakdowns of causality suggest that black holes might represent natural laboratories where the deepest principles of physics become accessible to mathematical investigation, even when they remain forever hidden from direct experimental observation by the one-way nature of the event horizons. Only took 58 years after the first theoretical prediction of black holes for astronomers to capture direct images of event horizon shadows, confirming that these mathematical monsters do indeed exist in nature while simultaneously revealing how much mystery remains about their internal structure and quantum properties. The successful imaging of supermassive black holes demonstrates both the power of theoretical physics to predict exotic phenomena and the limits of observational science when confronted with objects that hide their most interesting properties behind barriers that prevent direct investigation. The quantum nature of black holes suggests that they might possess forms of consciousness or information processing capabilities that transcend anything found in biological systems or artificial computers, operating according to principles that bridge the gap between mind and matter in ways that current science cannot adequately describe. The vast information storage capacity of black holes, combined with their complex internal dynamics and quantum entanglement with external systems, creates conditions where new forms of organization and computation might emerge through processes that remain completely alien to human experience and understanding. The connection between black holes and thermodynamics reveals that these objects possess temperature, entropy, and other properties normally associated with thermal systems, suggesting that they might represent natural heat engines that convert gravitational energy into more fundamental forms of order and organization that operate outside the familiar framework of chemistry and biology. The thermal properties of black holes create possibilities for energy extraction and information processing that might power civilizations capable of manipulating space-time geometry according to principles that transcend current technological understanding. The role of black holes in cosmic evolution extends beyond their influence on galactic structure and star formation to encompass their potential function as cosmic recycling systems that preserve and transform information across cosmic timescales that dwarf the lifetime of individual stars, planets, and biological species. If black holes do serve as information processing and storage systems, then they might represent the universe's long-term memory banks, where the complete history of cosmic evolution becomes encoded in quantum correlations that persist long after the matter and energy that created them have undergone fundamental transformations. Recent theoretical developments suggest that black holes might represent transition zones, where the familiar laws of physics give way to more fundamental principles that govern the behavior of information and consciousness at scales where the distinction between observer and observed becomes meaningless. These ideas point toward forms of physics that transcend the subject-object duality that underlies current scientific methodology, suggesting that understanding black holes might require new ways of thinking about the relationship between mathematical description and experienced reality. The profound mystery of black holes might ultimately point toward the limits of scientific understanding itself, revealing aspects of reality that transcend the capacity of rational inquiry to fully comprehend through mathematical analysis and experimental investigation. These cosmic enigmas exist at the boundary between known and unknowable, serving as constant reminders that the universe contains depths of mystery that might forever exceed human comprehension. Regardless of how sophisticated our theories become or how powerful our observational instruments grow over the centuries of continued scientific investigation, the mathematical singularities that lurk at black hole centers represent points where the equations of physics cease to provide meaningful predictions, suggesting that reality itself might contain aspects that transcend mathematical description and rational analysis. These infinities in the theoretical framework point toward the possibility that some features of the universe operate according to principles that exist outside the domain of scientific investigation, remaining forever mysterious despite our best efforts to understand them through empirical observation and theoretical modeling. Perhaps black holes represent cosmic koans that challenge us to transcend conventional ways of thinking about space, time, causality, and existence itself, serving as natural meditation objects that point toward truths about reality that cannot be captured in words or equations, but must be contemplated in silence and wonder. The profound questions they raise about the nature of information, consciousness, and the relationship between mind and matter might require forms of understanding that integrate scientific knowledge with wisdom traditions, that explore the deepest mysteries of existence through direct experience rather than analytical investigation. The eternal nature of black holes, which persist long after the stars that created them have exhausted their nuclear fuel, and the galaxies that contain them have dispersed into the expanding void, suggests that these objects might represent permanent features of cosmic architecture that will outlast all familiar forms of matter and energy. As the universe expands and cools over trillion-year timescales, black holes might become the only remaining structures that preserve information about the complex organizational patterns that once characterized the era of star formation, planetary systems, and biological evolution. In the far future, when proton decay has dissolved all atomic matter and only black holes remain in an ever-expanding, ever-cooling cosmos, these cosmic mysteries might represent the final repositories of all the information that was once encoded in living systems, technological civilizations, and the vast networks of galaxies that currently fill the observable universe. The slow evaporation of black holes through Hawking radiation would then represent the universe's final act of information processing, gradually releasing the encoded history of cosmic evolution into the quantum vacuum as space itself approaches maximum entropy and minimum temperature. The deepest mystery of black holes might lie not in their exotic physics or their role in cosmic evolution, but in their function as mirrors that reflect back our own limitations and assumptions about the nature of reality, forcing us to confront the possibility that the universe contains aspects that will forever remain beyond human understanding. They serve as constant reminders that scientific knowledge, however sophisticated and successful, represents only a partial glimpse of truths that extend far beyond the reach of rational investigation and mathematical analysis. Perhaps the greatest lesson that black holes teach us is that mystery itself represents a fundamental feature of existence, rather than merely a temporary limitation of human knowledge that will eventually be overcome through continued scientific progress. These cosmic enigmas point toward the possibility that wonder, awe, and intellectual humility might be more appropriate responses to the deepest questions about reality than the confident assertions that characterize much of contemporary scientific discourse. As we contemplate the profound mysteries that black holes represent, we find ourselves standing at the edge of human understanding, gazing into cosmic depths that challenge every assumption about the nature of space, time, matter, consciousness, and existence itself. These regions where physics reaches its limits and mathematics encounters infinities serve as gateways not just to other universes, but to entirely new ways of thinking about what it means to exist in a cosmos that contains mysteries profound enough to humble even our most sophisticated theoretical frameworks and observational technologies. The black holes that drift through space in perfect silence, invisible except for their gravitational influence on surrounding matter and the subtle warping of light that reveals their presence to our most sensitive instruments, continue their eternal dance through cosmic time, carrying with them secrets about the nature of reality that might remain forever beyond the reach of scientific investigation. They remind us that the universe is far stranger, far more mysterious and far more wonderful than even our wildest theoretical speculations can adequately capture in words or mathematical symbols. The cosmic questions raised by black holes drift through the expanding universe like silent sentinels, patient guardians of mysteries that may outlast the very concepts of space and time that define our current understanding of existence. These dark regions where matter disappears and information dissolves into quantum uncertainty continue their slow gravitational dance, spinning quietly in the void while space itself stretches toward ever greater emptiness and ever deeper cold. Perhaps the answers we seek about gateways to other universes, about the nature of consciousness and information, about the relationship between mind and matter, exist not in the interior of black holes, but in the silence that surrounds them, in the patient acceptance of mystery as a fundamental feature of existence, rather than as a temporary limitation to be overcome through analysis and investigation. The event horizons that mark these boundaries between known and unknowable expand and contract according to laws that transcend human comprehension, encoding information in quantum correlations that span cosmic distances and temporal scales that dwarf the brief moment of awareness that constitutes individual consciousness. These boundaries exist not as barriers to understanding, but as invitations to wonder, pointing toward depths of reality that can only be approached through silence, contemplation, and the gentle release of the need to know. In the absolute stillness of intergalactic space, where black holes drift through the expanding void like islands of infinite curvature in an ocean of gradually cooling space-time, the deepest mysteries of existence continue their patient wait. They require no answers. demand no solutions, seek no resolution, they simply exist, perfect in their incomprehensibility, eternal in their mystery, serving as cosmic reminders that some truths transcend the boundaries of language, mathematics, and rational thought. The universe sleeps on, carrying its secrets through the long night of cosmic expansion, while black holes keep their eternal vigil at the boundaries of space and time. Where wonder meets mathematics and silence encompasses all possible knowledge, in their patient darkness, all questions find their rest.